guys, what is up? Steel of a Feather here, and welcome back to my channel. Today, we're going to be talking about two things. This is going to be a fairly long video. We're going to be talking about the golden ratio and Lucas numbers. So, first, the golden ratio. The way we're going to be talking about this is it involves the Fibonacci sequence, and if you don't know what that is, I made a video on it, but I'll go over it real quick. It starts with 1, and then 1 again, 2, and then 3, and then 4, and then 5. Okay, I just got like really loopy. There's no 4. 5, and then 8, and then 13, and then 21. Oh, that looks like a 4. 21, 34, 55, and so on. So, the rule for this is x to the nth place, of the number in the nth place, so that's just any number, equals x to the nth place minus 1 plus x to the nth place minus 2. So if we started here, this is x to the 1, 2, 3, 4, 5, 6, 7, 8, 7. So this is x in the 7th place. So minus 1 is this, minus 2 is this. So you add those two together. This one right here is x to the n minus 1, and this right here is x to the n minus 2. So you add those two together, you get x to the n or to the 7. So, yeah. So the way to find the golden ratio, focus. Okay. So the ratio for this is hold on. X to the n over x to the n minus 1. That's the ratio. So we're going to solve for the golden ratio. That means that this means that we can simplify this or change it to x to the n minus 1, x to the n minus 2. So that's not the golden ratio, but this is how we find it. This is how we find the golden ratio. Sorry if I can't hear me. So yeah, we're gonna call this ratio. We'll call it. How about delta? We'll call it delta. Lowercase delta. You can't. Can you see it? Yeah, you can. So now what we do. So here with the first one. Oh, where's my pen? Right there. This first one, I'm gonna write a little bit bigger so you can see. Like that. This first one. We already know what x to the n is. It equals this. So we'll write that again. X to the n minus 1 plus x n minus 2 over x n minus 1. So now we can simplify this down. Oh, you can't see it because there's two of the same thing right here. Sorry about that. So if we have two of the same thing, we can just simplify this down, and it's really easy to do that. So we can simplify it down to 1 plus x to the n minus 2 over x to the n minus 1. And then we simplify that down again and get x to the n minus 1 over x to the n minus 2. Because we just inverse it. And that still equals delta. That's a really bad delta. Sorry, you couldn't even see that. That's what we just did. So that means that 1 plus the inverse of this ratio is the same thing. So we can just change this to 1 plus 1 over delta. And that equals still delta. So yeah, now that we have this, we can just keep going on. And so now we're gonna use a little bit of the quadratic equation. So if we can just rewrite this, rearrange the formula to delta plus 1 equals delta squared, and that's true. So now we can just simplify that even more to delta squared minus delta minus 1 equals 0. And with the quadratic equation, or the quadratic formula, we always know if you have a to the x squared plus bx plus c that equals 0, then we know that x equals negative b, that's a 5, negative b plus or minus the square root of b squared minus 4ac over 2a. So we can just start plugging this in. Sorry, I didn't show you guys that. That's the formula. So if we just start plugging that in. So now, if we just start doing this, then we know that delta equals 1 equals, let's see the first one, negative b. So this is b because b is the coefficient. So 1 plus or minus the square root plus or minus the square root of, what is the next one, b squared? Yeah, b squared. So b squared 1. Negative 1 squared is just 1 minus 4ac. So 4 times negative 1 times the c is just, that's just 4. Over, what's the next one? 2a. So 2a is just 2. So that means that delta equals 1 plus or minus the square root of 5 over 2, because that equals 5. And now that on a calculator, oops, oh god, we're gonna have to go into the next page. Anyway, it'll equal 1.618033988, blah blah blah, forever, infinite. The Fibonacci numbers are not the only numbers that show this ratio. In fact, a lot of people relate Fibonacci to the golden ratio. That's not good, because there are a lot of other sequences that show the golden ratio. So when you think of the Fibonacci sequence, like I said, you think of 1, 1, 2, 3, 5, 8, 13, and forever, right? Lucas numbers are a little bit different. These are, yeah, this is where we're going to talk about Lucas numbers. By the way, we got the memo. Lucas numbers. So, his numbers, well, if you if you want to do a different derivative of the Fibonacci numbers, you might want to try to start with 1, not start with the 1, 1, and then just go 2, but you have that right here, so you're just starting a little bit forward, so you'd still get 3, 5, 8. What he does is he switches them around. He goes 2, 1, and then from that you go on like the Fibonacci sequence. You go 3, 4, 7, 11, 18, 29, and so on. Those are Lucas's numbers. So his numbers have a lot stronger relation to the golden ratio. So anyway, this is how we're gonna prove it. So the symbol for the golden ratio, I believe, is like that. So if we do that, the golden ratio equals, once again, I wrote it down over here, 1.6803398, like that. There's supposed to be a 1 right there. So that's the golden ratio. Oh, you can't even see that. Okay, that's what the golden ratio equals. But if we take the golden ratio squared, that'll equal, oh, I just move this over a little bit. That'll equal 2.61803 infinitely. And if we round that up to the nearest whole number, here we'll round this one up 2. If we round that up, we get 3. We're not going to round that. And now if we take the golden ratio cubed, we should get something like, hold on, times 2, times 4.23606. Yeah, that seems right. And forever. And if we round that up, we get 4. Or if we round that to the nearest whole number, we get 4. And I'm already seeing a pattern here. I don't know if you are, but we'll do a couple more steps. So now if we do golden ratio to the fourth power, we should get something like, hold on, 6, 1, 8, 5, 4, 1, 0. Yeah, forever. That'll go on forever. Round that up. What do we get? 7. So, we'll do one more to the 5. And to the 5 equals something like 1 times fucking mother. Ugh. I don't like this. Okay, to the 5. Oh, I didn't put the 5. 1 times 11.09016, I believe. Then we round that up, we get 11. So, take all those numbers, and if you haven't seen it yet, the order is 3, 4, 7, 11. Now, where have you seen those numbers before, huh? Right up here. Right there. And if you keep going, you will get every number of the Lucas sequence. So, this doesn't really have any explanation of how we found the golden ratio. That's all Fibonacci and his partner, which I don't know his name off the top of my head, but he had a partner right now. So yeah, that's the Lucas numbers. They have a lot stronger relation, and I don't know why he got the idea to switch around the 2 and the 1, but it works, and yeah. So a lot of people are confused by the rounding up. How, like, what the heck? It's math. You're not supposed to have to round up. But the farther you go up, the closer you actually get, and the less you have to round. It's hard to explain. So yeah, today learned that the golden ratio, it equals 1 plus the square root of 5 over 2. And that's important with a lot of things, through like mathematics and geometry and stuff like that. Good thing to know. Hope you guys enjoyed. If you did, make sure to leave a like, comment, and subscribe. Comment some more topics I should talk about, and comment some ideas. Maybe comment if you've tried this, if you would like to learn more about this. So yeah, goodbye.